Hello, and in the last of these talks about electrons in solids, I want to talk about insulators, and in particular dielectrics and capacitors. The element I've been using as my example of an insulator is sulfur, not a particularly common component in electronics, but it is an insulator because the valence band is completely full, the conduction band is a long way above the valence band, so even at high temperatures the valence band is completely full and the conduction band is completely empty. The Fermi level halfway in between, and since there are no electrons in the conduction band and no vacant states in the valence band, nothing can move. It's an insulator. So if it doesn't conduct electricity, why is it interesting for an electronic engineer? Well, because it does react to electric fields. While the electrons are not free to move throughout the lattice, they are bound to their local atom, the orbits can be distorted by an external electric field. Kind of works a bit like this. This would be an atom with no electric field. If you put on an external electric field, then the nucleus, which is positively charged, is repelled by the electric field and pushed this way, whereas the electrons, which are negatively charged, are attracted to the source of the electric field and experience a force this way. While the electrons cannot break away from the nucleus, they can move their centre of probability, their average location. So we end up with an atom which has an average positive charge at the nucleus and an average negative charge at the centre of the electron's orbits, which is some little distance away. In other words, we've got a dipole. And every atom in a big block of the insulator will be acting like a dipole. All of these dipole fields build up, and this dipole creates an electric field in this direction, from the positive to the negative, which is in exactly the opposite direction to the externally applied electric field. The sum of all of these little dipole fields is called the polarization field, and it acts to reduce the electric field actually inside the material. So we have an internal electric field here, which is in the same direction as the externally applied electric field, but is smaller in magnitude. It has been reduced by the effect of the insulator and all these little dipoles within it. And that turns out to be very interesting if we're designing capacitors. Consider, we know that for capacitors, the excess charge on one plate of a capacitor is related to the capacitance by Q equals C, the capacitance in farads, times V, the voltage difference across the capacitor. Now, the voltage difference from one plate of the capacitor to the other is related to the electric field between the two plates by the voltage is the electric field times the distance. It's a similar formula to the one we saw before when we were talking about the Drude model. Electric field is a force on a unit charge. Force times distance is energy or work, so that is the amount of energy required to move a unit charge through that distance. But the amount of energy required to move a unit charge through a distance is also the potential difference between those 2 points. So it's equal to V, this quantity, the voltage across the capacitor. So I could write Q equals C times ED, where that's the electric field strength between the plates, and that's the distance the plates are apart. Or to put it another way, the value of the capacitance is Q, the excess charge on the plate, divided by E times D. And this suggests that if I can make the electric field between the plates smaller, I can increase the value of the capacitance for the same physical size of component. And that's exactly what you can do. And the way to reduce the electric field between the two plates is to put an insulator between those two plates so that the polarization field in the insulator cancels out as much of the electric field as you can. It's a very important and useful technique. Just about every capacitor will have some form of insulator, called a dielectric, between its plates, so that the electric field between the plates is smaller than it would be if there was just air between the plates. And this increases the capacitance in the same volume of component. Right, that's all I wanted to say about electrons in solids in this module. It's all you need to know for now. Those of you studying nanotechnology will learn a lot more later on in your degree programs. But for now, and for this module, that will do.